Hello, I got into a conversation with a few people about the mismatch between the observed distances measured at various latitudes and calculating the radius of the circle around the North Pole if the Earth was flat versus if the Earth was round, even going so far as to pick a couple of places. So in this case, I chose one town. Here's the latitude and the longitude coordinate for it. And I also picked Nueva Loja, latitude, longitude, and I picked this one on the map just to show you where it is. So it's going to be in Ecuador. And the reason why I chose these two places was because it's very close to the equator. And there's a road, E10, and here's an E45, and I think it was this other town over here somewhere. So it's a road that goes east-west, and anybody can take a car and drive from one town to the other. And to see just how far it is on the odometer, I just used Google Maps to measure the distance, and it measures a roughly 37 kilometers. So because the latitude is roughly the same, I just subtracted the one longitude from the other to get me a difference in longitude, and that's the angle that I'm using. To get the measured circumference of the Earth around the equator, I just took that 37 kilometers, multiplied it by 360, and divided by the difference in that longitude, and that gave me 40,000 kilometers. In this cell, I decided to calculate how many kilometers per degree there should be, so I just simply divided the distance, 37 kilometers, by the difference in the longitude, or 0.325 degrees, and it gave me an estimated kilometers per degree of 113.77, which is pretty close. It's really 111. To get the distance to the North Pole based on these values over here, I took D5, which is my kilometers per degree, and I multiplied by 90, and that gave me 10,239 kilometers. And it's a little bit high, but it's in the ballpark. I then decided if the Earth was flat, and if, as flat earthers say, the distance on the ground is 60 nautical miles per degree of latitude, giving us 10,000 kilometers to the North Pole, what should I expect the equator circumference to be, being equidistant from the North Pole? So it's just a simple 2 times pi times radius, and that gives me an expected flat Earth equator circumference of 64,339 kilometers, far more than the measured equator circumference. And then finally, I decided, well, simply based on a measured distance that anybody in their car can do. I mean, 37 kilometers is not that far. All you have to do is just find a straight enough level road that goes east-west, work out your latitude. You can find out what the radius of the Earth is simply, in this case, by taking the estimated circumference around the equator, dividing by 2 and dividing by pi. And that gave me 6,518.95 kilometers, which is pretty close to 6,371 average kilometers Earth radius. So there's the R. Then I was going to do this as well. This is a spreadsheet given by US Airlines and gave the routes and the distance in miles. And so I thought I was going to use this as a similar exercise as this. I've already done this kind of analysis before, but here what I've done, this section uses the haversine formula to calculate how many miles are expected between two geocoordinates. So the airline has a route that goes from Orlando to Charlotte, and they claim 468 miles. And so I'm simply using this same value to derive the degrees on the Earth. Here I'm doing the same thing, and then I subtract this one from this one and take the absolute value, and that's this column here. And I also have conditional formatting, and you'll see the other one on the other side because it's a lot more. Then I took the flat Earth model and I took those two geocoordinates. Then I calculated the XY coordinates on a flat map, took the hypotenuse and calculated a distance in miles, derived a similar tag, and this time I took the difference, and now you can see the color coding is a lot more. Anything between a half a degree difference and 1 degree is going to be in yellow. Anything 1 or greater is going to be in red. So as you can see, this doesn't quite work out. I was getting ready to do this entire presentation, and I was even going to do a little bit more than that. And then Bob the Science Guy puts out this video and beat me to it. So I can't really do that anymore. So I'm going to have to find something else to do. I highly recommend you watch his video, and I'm going to put a card to it right about here. Very, 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 very entertaining. So I decided to do something else instead. Must have been at least 6 months ago. I made a video where I introduced the AE map on my Skywatcher app. I decided to tweak it recently. And so what I did was I added the extra calculations that flat earthers accept, which is 69 miles for every degree of latitude. And so I added a few extra features here that I'm going to show very shortly. But first I wanted to show it projected with where all of these objects are above the GP. And as you can see, it kind of looks like that. So I just put myself on Null Island right about here. There's my coordinates, by the way. But I also added a mode to project where things should appear if the Earth really was flat. And that's what all of this is going to be. So I'm just going to walk you through some of these entries. I chose the sun as the object to observe. If I were to say where the sun is supposed to be at this very moment, it would be right here, fast approaching South America. Based on my current location, being on Null Island right here, latitude 0, longitude 0, the sun should be at an altitude of 46.96 degrees with an azimuth of 234.989 degrees. So how high exactly is the sun? Is it 5,000 kilometers? There is no consistency as to the height of the sun. There is no consistency at all for the height of anything that appears in the sky if the Earth was flat. So I'm going to use 5,004 kilometers. And based on that, the distance between here and here should be 4,672.209 kilometers. If we use 111.195 kilometers per degree, based on the observed altitude and the object height of 5,004 kilometers to give us that distance, that should give us a zenith angle of 42.018 degrees or an altitude angle of 47.981 degrees. So it's 90 degrees minus this zenith angle. These calculations are based on the observed altitude like this. However, all objects in the sky move using a different set of coordinates, which is right ascension declination, and the right ascension is an axis of rotation that is parallel to either of the two celestial poles. And so what I did originally was I used that right ascension and declination to calculate where the sun should be on a flat Earth, and that would be this one over here. And at this point, this video is going to get fairly long, so I'm just going to skip this part, and it's going to be in the next video. The last thing that I did was I decided, well, where should be the sun for each of these 3 points? Is it over here where we would expect if the Earth was flat? Is it over here where we observed the sun by pointing something in the sky and measuring the angle? Or is it over here based on 69 miles per degree? So here, if I rotate for time, you can see this one follows the GP of real-world observations, but then there are 2 more that go off in completely different directions. This one is based on 69 miles per degree. This one is based on the azimuth and altitude readings that anybody can make at any location. And if you look very carefully, this one, the one that looks like a ring, lags behind this one until it gets to right about here at about 45 degrees maybe, and then it overtakes this one. I wonder where I saw that before. So that's going to be it for now. Thank you for watching. If you liked the video, I would appreciate the thumbs up, the subscribe if you're not already, and all of that other good YouTube stuff. And I'm going to see you again in another video soon enough. So bye for now.